All right, welcome back, everybody. How's everybody doing? All right, so I sent an email concerning the next exam, which opens up on Friday, and I extended the time as far as the range, so it will close up on Sunday to give you a little extra data to cover or to go over the chapters we're going to do today. The chapters we're doing today are fairly short. We'll knock them out. We'll be done with them very quickly. Well, fairly quickly. Okay. Other than that, the other email I sent out was this with respect to assignments that have been missed. I went back into my grade book on Canvas and put zeros to them. Again, I repeat, this does not mean that you cannot go back and do them. They are open. They're still open. I put the zero in there so you can see what your true grade is, because Canvas does not compute your grade, only compute your grade for those, Barbara, I'll get back to you here in a second. Only for those grades that have been, or those assignments that have been graded or completed. And so there's a lot of assignments that are past due that people haven't done, and that's okay. Just keep in mind, there's a time limit. Okay, and I did take off the penalty for the labs. Anyway, the bottom line is this: that shows your true grade at this time. So it did a drastic jump. So if your grade was up here and it went down, that's because there's missing assignments. And to give you a heads up in case you weren't aware of them, go back and knock them out, and so they out toward your grade. Okay. In the past, I would wait, and I mentioned this in the email. I would wait until the end of the semester, and so people were doing pretty good. Maybe they missed 2 or 3 assignments, and they said, "Well, I'm not going to do them," and unknowingly just left them alone. And so when I went back in there and I put a zero in there, their grade just took a dump, and and we were out of time for that individuals to do that exam or the assignment, and it wasn't good. So I do it early now, and so you won't be surprised if you decide to not do some assignments. That's the grade. Okay, there were some questions. Let me go through this. All right, Barbara has a question. We'll do that in a second. And Victoria, you're welcome. It's teaching online. We got to be a little flexible than normal, given all the circumstances of what's going on. But we got to do what we can. All right, now Barbara, your equation, I have H2 aqueous. I don't think you wrote the correct formula. Is that H2SO4, sulfuric acid?
Yes.
Okay, so you're balancing H2SO4. Yeah, we'll take a couple minutes here to do this one. And with sodium hydroxide. First of all, what type of reaction is that? Can anybody tell me that? Let me draw it out here. Okay, and we are taking H2SO4 plus sodium hydroxide. Yes, that is correct for Barbara and Skylar. It is an acid-base reaction, a neutralization reaction. We're having the hydroxide there, and then this is 2 protons coming off of the sulfuric acid. Okay, so I'm going to just draw the arrows here. So recall that it's the net reaction. That is what is actually happening is the proton reacting with the hydroxide. That is the net reaction of this whole thing. And so whenever you got an acid and a base, you always get water. Now, as I mentioned before, when you are balancing acids, an acid-base reaction, follow the hydroxides and the protons, okay? And so given that we have, this is the net reaction that was happening. You know, it takes one proton, one hydroxide to give me one water, right? One, and one. So with that being said, if I have 1,000,000 protons, then I need 1,000,000 hydroxides to neutralize those 1,000,000 protons, which will give me 1,000,000 waters, okay? Because the ratio is 1 to 1 to 1. And so here we have sulfuric acid with 2 protons. So what does that tell you? How many hydroxides do I need to neutralize the 2 protons coming from the sulfuric acid? Anybody know? I got 2 protons here, two protons coming from sulfuric acid. How many hydroxides do I need to neutralize those 2? Exactly. So I need 2 hydroxides. So that tells me right away that I can put a 2 right in front of sodium hydroxide, okay? And that being said, that means that I'm going to make 2 waters, okay? Because from the net reaction, 1 proton, 1 hydroxide gives me 1 water. I got 2 protons, 2 hydroxides, I get 2 waters. Now, all you're going to deal with is the salts. And so we got the sodium salt and now the sulfate salt. We got to put those together, okay? First, put them together as ions to make sure you put them together the correct amount, numbers of each. So the sulfate's SO4, and the sodium is an A+, right? We all know that because sodium ion is in, well, sodium metal starts in group 1, has 1 valence electron. When it becomes ionic, will be a +1. So this means that I need 2 sodiums for every sulfate. So its formula would be sodium subscript 2 SO4, okay, for sodium sulfate. Now we go back and check, are we balanced? Well, I'll go back overall. We got a total of 2 hydrogens coming from sulfuric acid and 2 hydrogens coming from sodium hydroxide. So we have a total of 4 hydrogens, do we not? In the reactant side, 4 hydrogens total. All right. So go to the products. Do we not have 4 hydrogens? We got 2 molecules of water that were generated. That is a total of 4 hydrogens. So hydrogens are, check that out, hydrogens are good. We got 2 sodiums on the reactant side. We got 2 on the product side. So sodiums are good, okay? And then we got 1 sulfate, SO4. On reactant side, and we got 1 sulfate. So would you say that this is balanced? I would say yes. And so the point of, balancing acid-base reactions here is this doesn't have to be a trial and error. Sometimes some reactions, when we try to balance them, it is a trial and error. But for acid-base reactions, follow the protons and follow the hydroxides, okay? Once you do that, the other counter ions that are with them will fall in place, okay? You got that, Barbara?
Yes, thank you.
Okay, no problem. All right, well,
I have one more question. I'm sorry.
What did you say?
I have one more question. So, could you say that every time when I'm in balance and there is a water, can I keep the OH together, or is it better for me to do the O and the H separate so that way I can see visually and do the count correctly?
I repeat the question. You kind of broke up from my end. Something that when you're balancing,
When I'm in balance occasion and there is water, so I should keep the OH together or apart?
Oh, always. The OH is a polyatomic ion. That hydroxide is an ion. You always keep that together.
Thank you.
Okay. Yeah, it's together now. Not to be confused with the OH of water. Okay. You got OH with the sodium hydroxide, which is the hydroxide ion. And yes, water has an OH, but OH in water is covalent. It's not an ion. Okay. It's not an ion until a proton is removed from water. When you remove a proton, now you have the hydroxide. So there's two different entities there.
Sir,
All right. Yes.
I may know why she's asking that, because on the videos with Dr. Kim on the acid base equation, she says you can think of it as HOH to help balance it. Maybe that's why she's asking.
Oh, okay.
That's
Well,
correct.
Yeah. Okay. Let me do it this way. All right. So back. So the hydroxide here. I mean, do we agree? Oh, all of Dr. Kim's videos are on the modules. If you look at the modules for all the chapters, you'll see videos in there. Just click on that and you can send you right to that site. Okay. As compared to the videos for this class that are on a separate YouTube channel. Yeah. And she does have a YouTube channel also. Yeah. Now there's two types of videos, guys. There's the videos that have been pre-made concerning these chapters, and those are Dr. Kim's that we all incorporate into our lectures. And then there's the videos that are made here when we are doing the lecture. So you get a double whammy of the material, if you will. Okay, now with respect to the OH of water and the OH of the sodium hydroxide. And so if we draw out water, obviously we have this symbol. Now, whatever it takes to help you understand or to balance, I mean, you can treat the OH separately. If that is you should keep it separately, I mean, together, OH, because it's a polyatomic ion. But if that is not working for you, then I guess you can go ahead and separate it to help you balance it. All right, so exactly, Odette, like I mentioned, all her videos are incorporated into our module. So if you not touch the modules, go into our modules, every chapter, you'll see the videos, Dr. Kim's video. All right, so when I say to help you balance, you follow the proton and follow hydroxide. That will assist you. That will help you with respect to balancing or to creating the right number of waters. And by default, those hydrogens and those oxygens rebalance. So once you follow the proton and the hydroxide, your water and oxygens are automatically balanced. Because here we needed 2 protons, right? And 2, I mean, look at the general net reaction. 1 proton, 1 hydrogen from hydroxide gives you 2 hydrogens, right? There are 2 hydrogens in water. 1 oxygen coming from the hydroxide, we got 1 oxygen. So water is automatically balanced as you follow the protons. Okay, so now the only concern you have to worry about is the other counter anions and balance those out. And that's why I always write them out first as ions before I put them together. Once I do that, then that gives me the correct formula. And 9 times out of 10, by default, everything falls in place and you don't have to, everything balances itself out. Okay, so maybe it's this way. For acid-base reactions, follow the protons and hydroxides to help you make sure that you got the proper. Yeah, I'll answer that question in a second, Claudia. Follow the protons and the hydroxides. Give the proper number of waters that are being created. Then from there, work on the counter ions, which will be the cation and the anion of the acid and the base. Write those in the proper formula. And like I stated, 9 times out of 10, they will by default balance each other out once you do that. Okay. Now the question here, does proton mean a positive charge element or just H plus? Okay. A proton is a hydrogen atom that has lost its electron and now becomes a positive charge ion. Okay. Hydrogen is very unique in that it can lose that one valence electron, or it can gain one more electron because that one orbital has room for 2 electrons. So it becomes either losing electron becomes a proton. If it gains an electron, it's now called hydride. Okay. All right. Barbara, I hope that helps your question. I hope I didn't muddy up the waters there.
It helps. Thank you.
All right. So any other questions before I move on? All right. Well, thermodynamics. What we're giving you here is like the tip of the tip of the tip of the iceberg with respect to this area in chemistry / physics. Okay, thermodynamics. If you break that word down, you're talking about thermal meaning heat, meaning coming from energy, and dynamics is how things operate, the overall movement of things, how things operate. With respect, in our case, with chemistry, there are scientists that's their whole area of thermodynamics, and they study things. My initial months of being in graduate school, my research had dealt with the kinetics, how reactions react, and try to study reactions and determine how things happen. Now, we tend to think that we simply just take reactant A and B and just put them in a beaker and magically some Harry Potter stuff happens and the reaction proceeds. Okay, well, sometimes it does, but if certain things are not tuned in just right, reaction won't proceed. Okay, and that's what we're gonna talk about. We have in thermodynamics what is called collision theory. Here we have 2 reactants. It could be 2 of anything, but from the looks of it, it could be 2 different diatomic molecules. Okay, 2 different colors. All right. Well, they react together. Then they go through a stage in the center here where we're getting bond breakage and new bond formation and bond breakage. Okay, so this kind of intermediate, change the color here. This intermediate stage that really occurs quickly and doesn't hang around very long. But notice what we're doing. We got to break this bond here, and we got to break this bond here to create 2 totally different products. Well, we go through this area, this snapshot. If we can take a snapshot of going from point A to point B, where we are getting bond breakage occurring and bond formation, new bond formation. Notice the geometry has to be just right. Okay, because if the geometry of the 2 reactants is not correct, then we're not going to get a reaction. Also, what's important, they got to have enough energy, the sufficient minimum amount of energy for these 2 reactants to come together to give us product. And we'll have more to say about that in a second. But eventually, once we get A and B together, we end up with the new, totally new products. And it looks very straightforward and simple. And like I said, most of the time it is. And in us chemists, we work in the lab, we have a control environment. We generally are reacting, maybe 2 or 3 reactants are come together, maybe something else to help the reaction to proceed. And we get a product, and then we isolate it, analyze it, and go forth. But can you imagine your human body where you have just millions of different things happening there, different chemicals, different factors, and yet we're able to get reactions to proceed. Otherwise, we wouldn't exist as we exist. Okay. So it's quite fascinating field, this thermodynamics. All right. So bond breakage, bond formation. This particular area, this little intermediate snapshot of what's happening is called a transition state. Just thing in the brackets. It's temporarily. This is where we're getting, it's a hybrid area where we got, it looks like the product and it looks like the reactant because we're getting both bond breakage and bond formation. So we have this transition state that reactants go through. And there is a specific amount of energy necessary to attain that transition state. So we gotta have correct collision, okay? And without a successful collision, we are not able to make products. So one way to increase a collision is just by virtue of numbers. If we're reacting A and B together and we only got one molecule of each, and we got them in a beaker, imagine yourself in your room right now and we got 2 molecules. Imagine 2 balloons filled with helium bouncing around in your room, 2 different colors. And the idea they're going to come together to form a product. All right. Well, eventually they will. If they're in your room, they're going to, you bounce them around, they're going to get together. So but how can we increase the chances of that process of coming together? We add more balloons, right? Makes sense, right? Common sense. If I want to increase the chances of getting the reaction, increase the number of collisions, okay? And to do that, I may add more material, more balloons in my room. Maybe fill up the whole room with the balloons, like the 2 behind me. This red one and the blue one need to come together to create some kind of a new balloon, if you will. Okay. Another thing too, not only do they have to come together, they got to have enough energy for that process to occur. And what we can do is heat up the room a little bit. As anytime we heat something up, we give it kinetic energy and they start to move around. So moving around a little bit better increases the chances of these 2 balloons coming together and reacting to form a product. So increase the collisions by either adding more material or heating it up. Okay. We call that energy, by the way, is the energy of activation. That is the minimum amount of energy to activate that reaction to proceed to product. And orientation. The molecules must come together in this very specific orientation and angle. It is, if anybody shoots pool, then you know what I'm talking about. Or maybe you shoot billiards. I don't know. I shoot pool. So I got the cue ball. I got a ball in the corner. I got trying to make it to the corner pocket. I need to hit that cue ball with enough energy and the correct angle so that ball can get to the corner pocket and or the side pocket or wherever I'm going to do it. Now, if I do not give it enough energy, if I don't hit that cue ball enough energy, that ball may not get to the corner pocket. Or if I hit with too much energy, the ball may just jump off the table, okay? Or if I don't give it the right angle, I'm going to miss that pocket completely. And so there's a lot of variables involved there. They got to be orientated just right. So obviously, what this whole process leads to is called the rate of reaction. It's how fast this reaction occurs. Some reactions are very slow. Some reactions are very fast. Those fast reactions are AKA explosions, which is not a good thing. All right, so we increase the reactant, we get more reactants, we get more collisions, we increase the chance of making product, okay? We can increase the temperature, which causes the molecules to move faster, which then increase the probability of them coming together with the right amount of energy and the correct energy and angle and so orientation for them to make product, okay? Or we can add a catalyst. A lot of times reactions don't occur very readily, and they require a catalyst. Now, the thing about a catalyst, what they do is they're not directly involved in the reaction, but they assist the reaction by they lower that energy of activation that reactants must overcome to become product. So they lower it, so it doesn't take as much energy to overcome the energy limitation and get the reaction to proceed. Sometimes reactions can be, a catalyst can be very, very hazardous. We get tons of different types of catalysts in our body. A lot of reactions in our body would not occur. You know, they will occur, but it may take years for them to occur without the help of the catalyst. And so catalysts are very important in biological systems. I once in graduate school had a pretty big explosion. I was doing reaction kinetics, meaning I'm studying how reactions proceed and trying to follow the rate of the reaction and so forth. So I created a number of vials closed up, sealed up of the reactants, and the idea was to start them out, made the whole solution and spread them out amongst the vials, sealed the vials up, put them in a hot bath, constant bath, and then periodically take one tube out and analyze it. I just happened to do all that. Then as I put them all into the water bath, I took in a hood. We normally run the reactions in the hood for your protection of any fumes. But I took one step back and the whole thing blew up. And I'm like, whoa. So later on, I tried to figure out what's going on, and there was a trace amount of metal, iron fume metal in my containers. And they acted as a catalyst for this reaction, which meant that reaction proceeded extremely fast, so fast that it exploded, gave it too much heat and so forth. So catalysts can be good, they can be not good, depending on what they're doing. Again, as I mentioned, this energy of activation, as it is defined as the minimum energy needed to react, in other words, to turn reactants to products. Okay. We also have equilibrium reactions, and we touched on these on some of these weak acids and these materials that were insoluble. We have a double arrow to say that, you know, we got reactants on the left side and reactants on the right side. And so the double arrow just tells you that this reaction is reversible. And actually, there's a point where it will reach equilibrium. That is, the rate of the forward equals the rate of the reverse. A good example, an analogy would be a soda pop. If you take a soda pop bottle, plastic bottle, and it says about halfway empty, and you take it and you shake it up, okay? Obviously, the carbon dioxide goes out. Now, before that, you got your bottle. I wish I had a bottle here. And it's in steady state. It's an equilibrium state. That carbon dioxide, there's a lot of it in the head, in the air area of the bottle, and a lot in the solution. So it's going back and forth, you know, so the gas is going from the air into the liquid, back and forth. There's an equilibrium state. As I take that bottle and I shake it off, what happens? Carbon dioxide goes out of the liquid and goes into the air. Pressure builds up. Obviously, you don't want to open up that bottle, right? But if you take that bottle and you let it sit, eventually the system goes back to equilibrium, so it's safely you can open the container. And that's what an equilibrium reaction does. It's a state where nature wants to maintain an equilibrium, and it does everything it can to go back to an equilibrium state. your pH of your blood is one of those examples. There's an equilibrium. It wants to maintain that pH of 7.4, 7.3, somewhere in there. All right. Next question. Exactly. Nature wants to be happy, and nature's lazy. It's going to take the easy way through things. Okay. It's always downhill. You can make nature go uphill, but you got to put energy into the system. Right. So we have energy profiles, and there is a diagram on the top right hand side. And what that diagram is this. What this shows is, let me just draw this. We can look at a reaction, and and follow it over given time. And so if we follow and do some measurement of energy, depending on how you set this up, we can create a graph. Okay. And the x-axis is basically time. Okay. So we can get a reaction, study it, do some measurements, and we can come up with this energy profile. And what happens is we start off with the reactants at some amount of energy. Okay. And so reactants start here. So these are I'm going to call those reactants. Now, as we go along and we follow this reaction, we're basically taking a snapshot over time. That's what we call that the reaction coordinate down here. We just call it time for right now. Okay, we take a snapshot of the reaction. And as it goes along, we're going to reach a point on top here that we call TS, and that is the transition state. Okay. Now, once the reaction is complete, we have created products, and the product's energy level could be, I don't know, maybe someplace here. So I'm going to call that P. And so all along here, we have data points that we can connect and give us this graph that looks up there like the top right. Okay. Now, as I stated, we have an axis here. So for example, maybe we started with 10 units of energy. So we got 10, 20, 30, 40, 50, and 60. So you can see that our transition state, I can't extrapolate very well, is somewhere in 60 units of energy. I start off with 10 units of energy. Right now, we're just using arbitrary units of energy. Okay. And guess what? Our products, when it's done, and when I extrapolate, extrapolate a line out to the graph, I don't know, this could be maybe 5 units of energy. You see how that works? So I got 3 points here. I got my reactant at an X amount of energy to begin with, my transition state, which is someplace up high energy, that we have product bond formation and new bond breaking and bond formation. And then at the end, the product is done. It could be down in this position. Okay. And all these are data points that we collected along the way, and we can make this graph. Well, if we take where the reactant started, and we go up to where the transition state is, this difference of energy is delta E, energy of activation. So that means 60 minus 10, the energy of activation is about 50 units of energy. Does that make sense? Because the transition state is at 60. We began at 10. 60 minus 10 tells us that's 50 units. Energy of activation for this hypothetical reaction was 50 units of energy. Okay. Now we have another factor we call delta H. You'll notice it here. And that basically is the amount of energy of the reaction. Okay. That's a specific name. We'll call that in a second. And that is simply the difference where the reactants ended minus the energy of the products minus the energy of the reactants. Okay. And the delta always is the change. Delta means change. So the difference between the products minus reactants. So in this case, the products ended up at 5 and the reactants started off at 10. So guess what? We have negative 5 units of energy. Crucial. That negative is very important. Okay. It's negative because that tells us that this reaction is what we call exothermic. Remember we were talking about energy loss and gain of energy from the environment where things got warm. Okay. When the product energy is lower than the reactant energy, we end up with an exothermic reaction and it gives off heat. All right. So that kind of trying to explain what that graph is up there. Okay. With some arbitrary units of energy in there to give you an idea of why things are negative and why things are positive. Right, let me clear this up and I'll continue. Okay, so transition state, that is the high point where we're getting bonds are breaking and bonds are being formed. Okay, very unstable species. It could exist, but it's like just flash. It's so quick it happens. Delta H is the change of the heat energy. People call it also the energy of the reaction. And that is defined as the product's heat / energies minus the reactants, like I stated. Product energy minus the reactants energy. If it's a negative, then we have a exothermic reaction. If it's positive, we have what's called the endothermic reaction. Remember, endothermic reactions, reactants gain or absorb heat energy, and it gets cold. And so heat energy is part of the reactants. Exothermic, it is heat / energy is part of the products. It loses energy, okay, and it gets warm. So heat exits the reaction, and we can designate that in these graphs. All right. So here the question is delta H positive or negative? Keep it in mind, delta H is the energy of the products minus the energy of the reactants. Notice that the product energy level is, let me draw that out a little bit straight. The product energy is at that level, and you can arbitrarily put units to this, and the reactants at that level. So you could say, who knows, you know, just put some arbitrary units, say this is 10 units, that's 20 units. All right, so we got 10 minus 20. So we have negative 10 units of energy for this reaction. That means delta H is negative in this example. What means reaction? RXA is a reaction, short for reaction, shorthand for reaction. Okay. So in this scenario, it's a negative value, therefore it's exothermic, and therefore it will give off heat. You'll be warm. Okay, let me clear this up. And so draw the energy for an endothermic reaction. Well, think about this. If in the exothermic reaction, the product energy level is lower than the reactant energy level, and delta H is product minus reactants, well, how can I make it into a positive value? How I do that is make sure that the final product energy level is higher than the reactants. That what you finally end up with, energy-wise, is at a higher level than where you started off as, right here. And so one could say, let's say maybe this is 10, maybe this is 50 units of energy, you know, in our scale here. And so here, products, which is 50, reactants, which is 10, that means that delta H will be equal to 40 energy units, a positive value, right? Okay. So this would be a positive value, simply because the energy, the final energy level of the products is higher than the reactants. Okay, so this slide here shows you the top one is an exothermic reaction, and the bottom one which shows you an endothermic reaction. Okay, remember that delta H is the difference between the level of the products and the reactants. So it sometimes when you do an endothermic reaction, that delta H may be a little bit, you know, confusing, but just remember that's just the energy difference between the products and reactants. That is delta H. Energy of activation is simply the difference between the top of the hill, the transition state, minus where the reactants began. Had nothing to do with products. And that energy of activation is the minimum amount of energy for this particular reaction to occur. If this reaction does not have that minimum amount of energy, no reaction will occur. Okay. It just requires that amount of energy. And sometimes you need to kind of heat up the reaction, but you got to be careful. You know, as a chemist, yes, you got to have enough energy to overcome the energy of activation. But if you heat it too high, sometimes it will decompose your reactants, and you're not doing the reaction that you want done. Something else is happening. Then you got to be careful. You might think, well, let's put a catalyst. Well, sometimes you got to determine, okay, what type of catalyst works. A lot of times metals work, but the question is it a elemental metal that will work, or is it an ionic metal? Catalytic converter that you have in your vehicle is a very classic example of a catalyst, very expensive catalyst, by the way. Hopefully nobody's taking yours from your vehicle. Okay. What the catalyst does is lower that energy of activation. So remember that we had the energy of activation here for normal. So we got E energy of activation from, say, normal, and then the energy of activation here for the catalyst, okay? And it's lower. So the energy may be enough from the environment, just room temperature, for this reaction to proceed, that it can occur very quickly, very rapidly. Once the catalyst is done with the reaction, then it goes on and helps another set of molecules. And it does this in multiple ways. Sometimes it just, the catalysts are very big catalysts, where is the ones I know, the enzymes in your body are essentially putting the two reactants closer in the correct orientation so they can react. And sometimes catalysts just lend more electrons into the environment so they can, reaction can proceed a little more readily. They function a little bit different, but the ultimate goal eventually is to lower the energy of activation. Okay, guess what, guys? Congratulations, that's it. So basically for this particular chapter, the takeaway is this: take a look at the graph, be able to identify those where the reactants are, where the products are, where the transition state is, what is the energy of activation, what is the delta H, those major components there. And also the other takeaway is finally, can you determine by the graph alone Is it an exothermic reaction or an endothermic reaction? Okay. And that's about it, really. Like I said, this is the tip of the tip of the tip of the iceberg. It's very, very small. All right. Tell you what, guys, finished a little bit early. Let's take maybe a 10-minute break. Okay. I got 10:46. Let's go to, well, just call it. Come back at 2 o'clock. Okay. Okay. Let us continue the next chapter. As I mentioned earlier with the chapter 11, those are the takeaway points. And basically looking at the graph, find the position of the reactants, products, energy of activation, transition state, and delta H, and then determine whether something's exothermic or endothermic. Okay. All right, now chapter 12. We're going to talk about mole. No, we're going to talk about the mole. Now, a lot of students in the beginning have a challenge with this, okay? But I want you to think of the mole very analogous to the way you think about a dozen. What do you think when number-wise, when somebody says a dozen, what is the first thing? What is whatever number comes to you? What is it? It's a 12, right? Or baker's dozen, exactly. I like the baker's dozen, especially when it comes to donuts. That's my downfall, donuts. So, well, the mole is nothing more than a number. Okay, let me repeat that. The mole is nothing more than a number, just like a dozen is, except it just happens to be a very big, big, big number. How big? Well, 6.02 times 10 to the 23rd number. Okay, big. So you got a big scientific notation number here. What does that tell you? I got to use my calculator probably, right? Yeah, so going back to your calculator to refresh your memory on how to use scientific notation. Now, this number is we also known as the chemist dozen or the physicist dozen, whichever way you want to look at it. But it is a number that describes, it could be a mole of atoms, a mole of ions, a mole of potatoes, a mole of apples, a mole of whatever. That mole consists of 6.02 times 10 to the 23rd of those items. Just like if I said a dozen atoms, you would think 12 atoms, right? Or unless it's a baker dozen of atoms and it's 13. Okay. 12 ions. Okay, same concept, same scenario, similar scenario, I should say, except the magnitude, the number is different. That's all. That's all it is, just a big, gigantic number. And I think that because it's such a big number, it kind of freaks people out and they're like, whoa, I don't comprehend it. Okay. But we'll go through it in a second. All right. So where did this thing come up? Well, this crazy looking character here on the right-hand side, his name's Avogadro, scientist, way back when. He came up with this number. 1 second, please. Okay, I'm back. Anyway, Avogadro came up with the number that's named after him, and it has the symbol N, capital N, lowercase a for Avogadro. It's just a super large number, 6.02 times 10 to the 23rd. Okay. Now, how big is this number? To give you a perspective of how big this number is. If you can see to the left, it is 602 sextillion. What does that mean? Well, if you were to count one number per second, 1, 2, 3, 4, 5, 6, 7, 8, etc., it would take that number of years to get to the end of that number. It would take 19 quadrillion years to finish counting that number if you were doing one number per second. Okay. I also gave you some other units there to give you an idea where you're at. So we're 1 billion 9 zeros, trillion 12 zeros, so on and so forth. All right, so that's a big number. It's a humongous number. Okay. Some more aspects about the mole. And if you had to give you a perspective on the size, if you had 1 mole of softballs, normal softballs are probably slightly bigger than a baseball. Okay, it would, all of them together would be the size of Earth. Okay, but these atoms are tiny. Okay, and it's really fascinating when you think about this for a moment. That remember the atomic weights of the periodic table, and I stated that on that periodic table they had units, the atomic weights at that time. Let's go back to it. Okay, so if we take copper for carbon, for example, which is right here, its atomic weight is 12.01. Well, the question is, what 12.01 what? Well, here comes the units. The units are grams per mole. Okay. 12.01 grams of carbon will contain 1 mole of carbon atom. Okay. Go over to nitrogen. Nitrogen has an atomic weight of 14.01. If you were to go to the lab and you had access to nitrogen atoms and you weighed out 19.01, you would have 6.02 times 10 to the 23rd atoms of nitrogen, or 1 mole. Okay. Nitrogen is a gas, by the way, so it's really N2, so it would be like 28.02 grams. So if you were to weigh out 28.02 grams of nitrogen gas, you would have 1 mole of nitrogen atoms. Bromine. Weigh out 79.90 grams of bromine atoms. You have 1 mole of bromine atoms. Since it's diatomic, you got to double that. So it'll be like 160 some grams per mole for the diatomic ones, because that's what they exist as in nature. Oxygen, the same thing. If I had just pure oxygen atoms and I weighed out 16 grams of it, I have 1 mole, or 6.02 times 10 to the 23rd. Okay. All right. So that's the thing about the units, that they have the units of the atomic weights. They have grams per mole. So if someone said to you, all right, you weighed out 4 grams of helium, how many moles do you have? Obviously 1 mole, correct? If you weighed out 8 grams of helium, how many moles will you have? Exactly 2, because we know that every mole weighs 4 grams. Brings me to the point. Since we have, let me go to the whiteboard here real quick. since carbon grams per mole, I have a ratio. Remember, I said the atomic weights have units. They're nothing more than a ratio. I can write that ratio with grams in the numerator, or I can flip it and say 1 mole to 12.01 grams. Every one of these I can do for all the atomic weights, because I'm going to use this ratio to calculate either, let me change the color here, to calculate either grams or calculate either moles, depending on what I start off with. Over here, I must start off with moles, right? Because my moles are canceled to give me grams. Over here, I must start off with grams because the grams are canceled to give me moles. See how that works? Okay, remember the ratios we were working with when we were converting units? I said, use this system here because here we are. We're using this ratio, the dimensional analysis, by keeping track of our units. Because down the road, we are going to be able to set up at the minimum of 3 conversion factors to get us from apples to oranges, if you will. All right. So on the periodic table, for example, carbon atoms, 12.01 grams, I have 1 mole of carbon. 1 mole of sodium atoms would weigh 22.99 grams. So on down the road. And the thing is, again, mole being just a number, it is a number for whatever units or entities you're going to use. So we could be talking about atoms, ions, molecules, formula units, potatoes, bananas, French fries, whatever. It's just a number, okay? Simply a number. And so one should be able to go to the table, periodic table, and if you're asked the question, how many grams in 1 mole of carbon? Well, we did that one already, 12.01. How many grams in 1 mole of gold? Well, 196.97 grams per mole. And for sodium, 22.99 grams. Really, that should just, the question says how many grams in 1 mole. The answer should be just grams, not just grams per mole. Okay. All of these have 6.02 times 10 to the 23rd atoms. Think about it. Think about it as eggs, small, large, and medium, right? You can go to the store, buy a dozen small, a dozen large, a dozen medium, a dozen large, and a dozen extra large, right? All of them have 12, but they're going to weigh differently, right? Of course, because of their size. And in this case, they're going to weigh different because of the number of protons and neutrons they have. Carbons have an X amount of neutrons. They all weigh up to an average of 12.01. Gold, being a larger atom, is going to weigh more. But they all have 1 mole. They all have 6.02 times 10 to the 23rd atoms, or 1 mole. Okay, so we need to learn to calculate the molar mass. Now, way back when, we had the formulas that we said, well, how many atoms of this, how many atoms of whatever we were analyzing? We ended up with, 10 carbons, 14 hydrogens, I don't know, 13 oxygens, something like that. We have to have you determine how many of each atom you had in this formula, okay? Now, here's why. Because now, once we determine how many atoms we have in each formula, using the periodic table, we can now calculate the molar mass for a compound. So the first thing we need to do is to write the formula. So here we are, writing formulas. We got the name barium hydroxide, okay? And so we need to write the formula first. This is an ionic compound. And so I need to first write them in ion form. So we know barium is a group 2 element, okay? It will have a +2 charge, so it is a B8 +2. Hydroxide is the polyatomic ion, it's the base, okay? It has a -1. Find that information on the, if you don't know it by now, go through the polyatomic ion table. of the periodic table. And it has a -1. That means we need 2 hydroxides for every 1 barium. Therefore, our formula would be as follows. Okay. All right, BaOH2. Now we know the formula. We go and determine how many atoms of each that we have. Here we have 1 barium, 2 oxygens, and 2 hydrogens. For the periodic table, determine the atomic weight of each atom times the number of those atoms we have. That and tally up the value. And guess what? Barium has an atomic weight of 137.33. Oxygen, 16 grams per mole. There's 2 of them in this formula. Hydrogen, each one is 1.01. So there's 2 of those, 2 hydrogens. Multiply those out, add them up. We have a molar mass of 171.35 grams per mole. Okay. How many atoms, if we were in the lab, and I said, okay, here's that bottle of barium hydroxide. Weigh out 171.35 grams of barium hydroxide. How many molecules of barium hydroxide would we have? Okay, let me try that again. We just determined that the molar mass of barium hydroxide is 171.35 grams per mole. If you were into the lab and you weighed out 171.35 grams of barium hydroxide, how many individual molecules of barium hydroxide would you have? No, not quite. Let's go back to that. If you weighed out 12.01 grams of carbon, how many atoms do you have? 6.02 times 10 to the 23rd atoms. If you weighed out 196.97 grams of gold, you have 6.02 times 10 to the 23rd atoms of gold. And if you weighed out 22.99 grams of sodium, you have 6.02 times 10 to the 23rd atoms. With that information, if you were to weigh out 171.35 grams of barium hydroxide, how many molecules of barium hydroxide would you have? The number of elements? No. 6.02 times 10 to the 23rd. That is correct, Skyler. Okay. That's how many. So everybody has a common factor, grams per mole. Back there, grams per mole. So if I weigh out 12.01 grams, I got 1 mole. All right. Another way to look at this, maybe, let's go back to the eggs for a second. Okay. I don't want to spend too much time on this, but I gotta do an analogy here. All right. And so let's talk about eggs. I like mine over easy. All right, so we got small, medium, and large. And of course, we're talking about 1 dozen, right? So we know that we got 12. Now, let's say, just for argument's sake, we just throw in a number out there. Let's say a dozen small eggs weigh 200 grams per dozen. Let's say the medium, let's just double it, say 400 grams per dozen. And the large, we'll double that, 800 grams per dozen, okay? Everybody get the idea here, right? Obviously, the small, medium, large eggs are all gonna weigh differently, because of their size. So all of these elements are going to weigh different. Hydrogen weighs it weighs a lot different than gold, right? But hydrogen, if I weigh out 1 gram of hydrogen, I'm going to have 1 mole, right? Because the molecular atomic weight of hydrogen is 1 gram per mole, 1.01 gram per mole. Gold was 196.7 grams. So if I weigh out 196.7 grams, I'm going to have 1 mole. All right. So let's go to the eggs. If I weighed out 400 grams of small eggs, can anybody tell me how many dozen small eggs I have? $44. Good. What if I weighed out 100 grams of small eggs? How many eggs would I have? 6, exactly. Because I know that every dozen, every 12 weighs 200 grams. Okay. And I can do the same analogy with medium eggs. If I weigh out 800 grams of medium eggs, I'm going to have how many? Dozen. 2 dozen, right? Because I know that each one weighs 400. So I'm going to have 24. And then the same analogy, if I weigh out 200 grams, I'm going to have half a dozen of medium eggs, and so on and so forth. Now, with that idea, if we go back to this here, here we got the small, medium, and large eggs. If I weigh out, say, 24.02 grams of carbon, this for argument's sake, 24.02 grams of carbon, do I not have 2 moles? Yeah, because I know that each one weighs 112.01. And that means if I double that, I'm going to have 2 moles. And if I weigh half of that, call it 6.005 grams, then I have half a mole. See how that's working? But the thing is that all is the carbon, the gold, the sodium. I weigh out 12 grams, I got 1 mole. If I weigh out 196.97 grams, I got 1 mole of gold. Sodium, I weigh out 22.99 grams, I got 1 mole. All of those will have that number of atoms. Now go to this. How many number of molecules of barium hydroxide would I have if I weigh out 171.35 grams? Do I not have 1 mole? Yes. Do I not have 6.02 times 10 to the 23rd molecules of barium hydroxide? Yes. Okay. All right. And now, if I do the same thing for the molar mass for water, H2O, I get 18.02 grams per mole. Think about this for a second. You weigh out 18.0 grams of water, just go in the tap water and weigh out 18.02 grams. I have 6.02 times 10 to the 23rd molecules of water. Now imagine all the water in the ocean. I couldn't even tell you to calculate how many grams that would be. But imagine if you were able to do that, you can determine how many moles of water you have out there in the ocean, and then it'll tell you how many molecules of water you have out there in the ocean. That's a lot of molecules. A lot of molecules. All right, so molar mass is important here because we need to figure out the total weight of that component, that formula. which is called the molar mass, which now has a units of 171.35 grams per mole, which I can write like that, or I can write it as 1 mole over 171.35 grams. Okay, remember that part. All right, Avogadro's number is a ratio. Okay, 6.02 times 10 to the 23rd atoms, molecules, bananas, oranges, whatever you want to count per mole. Just like the ratio of, it's no different. You just see a big number here, but it's no different than saying 12 units per 1 dozen, or 1 dozen over 12 units. Units could be whatever you're counting, okay? It just happens to be a very big number, and it is a ratio. I can't overemphasize. That's a lot. Yeah, that's true, Scott. There's a lot of water molecules. You just even calculate that number even for a gallon, 500 grams of water. You can see how that gives you a perspective of how small these molecules are. All right, so we can write that Avogadro's number in a ratio. And using dimensional analysis, we can keep track of units that help us to set up the problems correctly and allow us to do our calculations. For example, question here says, how many calcium atoms are in a quarter of a mole, 0.25 moles of calcium? Now think about that. It's like saying, well, think about it from an analogy, it would be like a quarter dozen of eggs. How many eggs do I have in a quarter dozen eggs? Can anybody tell me that? 3, exactly, right? Because a quarter dozen, which is 0.25. I just call it. I'll make it 0.25 dozen. I can set up the problem like this. Let's just use the eggs for right now. I know we're not going to problem, but just to use analogy. So if I go 0.25 dozen, and the question is, well, how many eggs is that? Well, what do I know? I know that in 1 dozen, there are 12 eggs, right? I set that up. Look at that. My dozen cancels because this factor, 12 over 1, can I write it as 12 over 1 or 1 over 12? I need it to be written as 12 over 1 because I want my dozens to cancel. And 0.25 times 12, guess what? That's 3, right? Well, we're going to do the same thing with respect to this, except that this factor just happens to be a larger number. That's all. Okay, and that's how we set that up. 0.25 moles of calcium times Avogadro's number, because that tells us the question is, we want the units atoms that we want. Those are the final units that we want, atoms. So 6.02 times 10 to the 23rd atoms per mole. Notice that our moles cancel, leaving us with atoms. So therefore, in a quarter mole of calcium, there are 1.51 times 10 to the 23rd calcium atoms. It's still a large number. It's still pretty large, but that's that number. Okay, keeping track of units. Here we're asking to calculate the number of moles if you start off with an actual number of molecules. Well, in this case, guess what? We need Avogadro's number written with the moles. We need to use this one because we want moles. That's what we're looking for in the problem, unit-wise, moles. So we set up our problem as follows. 3.75 times 10 to the 23rd divided by Avogadro's number tells us that we have 6,230 moles. Okay. Now, remember how to do your scientific notation here. It's either double E button, the EXP button, or the X10 to the X power button. Okay. Type in your numbers, refresh your memory, and how to use scientific notation. All right, so here we got here. Let's convert. We're going to do grams to moles. So we start off with grams, and we want to go to moles in our calculations. And we're going to use molar mass either as grams per mole, which is the normal ratio that we set up, or we can invert it as needed, depending on the problem. All right. So first question, how many grams is 1.667 moles of oxygen gas? Okay, let's look at this problem, analyze it first. We're talking about oxygen gas, okay? So that tells you that you are dealing with O2. Remember, oxygen is diatomic. The molar mass for oxygen gas would be 32.0 grams per mole, right? Because there's two oxygens, each one is a 16. And so here it asks you how many grams is 1.667 moles of oxygen gas. So let's write down what we're given. 1.667 moles of O2. Obviously, we need a conversion factor here of some sort because we want to get to grams. So our units, our final units are going to be grams of O2. Okay. So we start off in moles. We're going to need the molar mass, which we just calculated, but we want to make sure that we got moles in the denominator and grams in the numerator. And so we simply have to just plug that one in. Okay, because our moles of oxygen cancel the units of grams. Okay. So you see how we set that up? And we end up with 53.34 grams of oxygen. All right. Next one. How many moles is 45 grams of silver? All right, so we're talking about, now I almost use the words molar mass and atomic weight interchangeably, but it's not 100%. If you have a molecule, a compound of some sort, like H2O, we're talking about the molar mass. A molar mass generally means in general means the atomic weights of all the atoms of a compound. Here, we just have silver all by itself. It's not really a compound. It's an element, so we talk about atomic weight, okay? So the atomic weight of silver is 107. Let me look that up real quick, 107.87 grams per mole. Okay. And so that's what we need, the atomic weight of silver. And we start off with 45 grams of silver. And obviously, we need a conversion factor, and we need to get to moles of silver. Therefore, we need to set our conversion factor with grams in the denominator and moles in the numerator. Why? Because we want grams to cancel. And so moles is 1, and it's 107.87 grams. Okay? So we set that up properly. We checked our units. Now it's a matter of tapping into the calculator, and we end up with 0.42 moles of silver. So if you weigh out 45 grams of silver, you have 0.42 moles of silver. All right. Now, the important aspect about the mole is this: is we need to convert into moles when we want to go to point A to point B in our calculations. We always have to go through moles. That is the one factor that we can connect dissimilar units, if you will. How I can connect carbon with oxygen in a hypothetical reaction is not grams of carbon and grams of oxygen. The only way to connect them properly is to convert the grams to moles, and then from the moles go to moles of oxygen, and then from that goes to grams. So our factor that connects all the elements and all the reactants and all the products and so forth. Remember the ratio of those balanced chemical equations I talked about, the 1 to 2, 3 to 4, all those deal with moles and how we can get from bananas to oranges, if you will. So it's crucial that you understand how to calculate moles. Yeah, that's the only way we can get to a reactant in grams to grams of a product, and that is through moles. All right, so here asking you how many moles, how many grams is 0.055 moles of water? Well, we need the molar mass of water, okay, which you know is H2O as far as the formula. 2 hydrogens, 1 oxygen, which is 18.02 grams per mole. We set the problem up, okay, 0.0554 moles of water would weigh 0.998 grams, okay? And then how many grams is 4.75 times 10 to the 16 atoms of potassium? Well, here we got a little bit more of a challenge, you know, but still, nevertheless, you know, remember, we're talking about atoms now. Every time you see atoms, you need Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. You're going to need that factor. You're going to need the atomic weight of potassium, which is 39.10 grams per mole. That's from that is from the periodic table. All right, so let's write down what we're given. 4.75 times 10 to the 16 atoms of potassium. Okay, I need to get to grams of potassium. All right, so it looks like I'm going to need a couple of conversion factors here. First one, I'm dealing with atoms. So I can't use the atomic weight because the units of atomic weight are grams per mole. However, Avogadro's number is atoms per mole or ions per mole or whatever, but in this case, it's set up as atoms per mole. So I need to have atoms in the bottom and mole on top. Okay, and so that is a 6.02 times 10 to the 23rd for 1 mole. And look at that, my atoms cancel out. I'm good to go to the next step. Notice that I said if I need to get from point A to point B, I gotta go through moles because I converted atoms to moles with this factor here. Now I can get into grams. And so the next thing is I got to have grams in the denominator and moles in the bottom because I want my moles to cancel out. And that's 39.10 per 1 mole. Check my units, atoms cancel, moles cancel, leaving me with grams as far as the units are concerned. Okay, you had a question where? Which one would you divide? Gabriel, sorry. We will divide here because remember this is 4.75 to 10 times 10 to 16 over 1. So we're going to take that, divide it by Avogadro's number, and then multiply by 39.1. Okay, Does that answer your question? Okay, all right. So this is just like we set up those problems that we did. We did conversion of units. You know, we had to do multiple conversion factors. Okay. All right. Let me bring up the other one. It's a lot clearer than my handwriting here. All right. So here we go. First one was Avogadro's number. So we're dividing the number of atoms divided by Avogadro's number, and then we're multiplying by the atomic weight of potassium. That means that we have 3.9 times 10 to the negative 6 grams of potassium. Think about that for a second. We have this humongous number of atoms. That's a big number, 4.75 times 10 to the 16. You know, move that decimal point over 16 times. That tells you how big, how many number of atoms we have. And yet, they only weigh 3.09 times 10 to the negative 6 grams. Most balances out there can probably go, you know, 4 to the 5th decimal place. There are balances that can weigh a little bit more accurate, but they're very expensive. You know, it's very tough to work with. It'd be hard to weigh this in a typical, this amount in a typical balance. But that small amount, which is probably less than the weight of a hair, has that number of atoms. It's just mind-boggling. You put your head around it. All right, getting close to the end here. Now, we talked about the molar mass. Now we have something called the molar volume, okay? Now, way in the beginning when we were talking about the physical states, one of the things about gases was they don't have a set volume. Unlike the liquid and the solids, they have a set volume, okay? Their shape can change and so forth, but they have a known volume. And we said at the time that gases do not, which is true. However, under certain conditions, they do have a known volume. And that's called STP, standard temperature and pressure. Only under these conditions, and I have to emphasize it, under these conditions with 0 degrees, okay, I'll write that down, STP, 0 degrees Celsius and 1 atmosphere pressure, which is roughly where we're at now, ballpark, 1 atmosphere pressure, and 0 degrees, that's, you know, freezing point. So under those conditions, 1 mole of gas occupies a volume of 22.4 liters. So let's take an example here of all these gases. We have hydrogen, chlorine, ammonia, xenon, and methane gases. We have 1 mole of these gases. Each of those gases would have 6.02 times 10 to the 23rd molecules of that gas, okay? Their molar mass obviously would be different because they're different atoms, different number of protons and neutrons. Remember the electrons? Yeah, of course the electrons, but their weight is they're minuscule. The weight of the electrons, if you recall, AMUs are 0. So the bulk of the weight comes from the protons and the neutrons. And so they're going to be different because they have different number of protons, different number of neutrons. So hydrogen, 2.02, chlorine, 38, ammonia gas, 1704, xenon, 131.29 grams, and methane, 16.05 grams. 1 mole, that's their weight for 1 mole of gas. Every one of these gases would occupy a volume of 22.4 liters per mole. Now, guess what? Liters per mole. It's another ratio. Moles per liter or liters per mole. Okay, another ratio that we can tap into and use. The key part about this is they have to be gases and they have to be at 0 degrees, 1 atmosphere temperature. They're going to have, if they don't tell you you're at STP or either say STP or say 0, 1 atmosphere, then this is not true and won't work. okay? Only under those conditions, and you have another conversion factor of 22.4 liters. All right, and that's our ratio, 22.4 liters per mole. 22.4 liters is conversion factor. That is a measured quantity. Therefore, could be a factor in your sig figs. Remember that. I haven't forgotten sig figs. Okay, so 3 sig figs could be a factor with respect if you use that factor in your calculations to give you your final sig figs. So you have to be at 0 degrees and 1 atmosphere. So let's do some examples. There's that ratio at STP. We can write it with liters in the numerator or put liters in the denominator. Okay. What question is here? What is the volume of 1.25 moles of argon gas at STP? And so you're given moles, 1.25. We bring in the 22.4 liters per mole. We want liters in the numerator. Why? Because that is what we're looking for. What is the volume? Okay. And so moles cancel out, leaving us with 28.0 liters. Now you think about it, it makes sense. Think about your numbers. You know, sometimes we tend to plug in the numbers in the calculator and assume that we plugged in the right numbers and not really look at our answer and think about the answer. Does that answer make sense? Well, if you think about it, analyze the answer. You know, we got 1.25 moles, 1.25 moles, 1.25. We know that in 1 mole, it has a volume of 22.4 liters, but we have a little bit extra, right? So our answer should be greater than 22.4 liters. And sure enough, you said 28. If you made the mistake and you divided, Victoria, yeah, if you made a mistake and you divided by 22.4 liters, your number is going to be very small. And so by analyzing your number that you started off with and what you expect as far as magnitude, you can understand. Yes, Skylar, thank you. STP stands for standard temperature and pressure. It's not the oil additive you put in your engine. Okay, and so think about the answer. Think about the answer that you get. Does it make sense? Okay. It really some thoughts. So some of these problems you might think, I would never use anything in my real life, and that's okay. You might not, but I'll give you a real life example where problem solving is very important. Okay. Now, and there was a situation where a person needed to have, it's a medical situation. You had half an hour to insert 100 milliliters of solution. So through a pump, an IV pump, okay? And the instrument had a rate that you input, which was in hours per milliliters. That was the rate that you input into your pump. Some of you are out there work as nurses, probably know what I'm talking about. Now, the infusion that needed to be put in had to be in 30 minutes. You had to put it in 30 minutes, and you had 30 minutes to insert 100 milliliters. And that's the situation. I had 3 nurses there argue with each other what the rate should be set up. And I kept telling them the answer, and they kept ignoring it and saying, no, that's not it. That's not it. That's not it. So anyway, the point being problem solving, you know, thinking about the numbers that you're working with. So think about that one. I'll come back and give you the answer. You got half an hour, 30 minutes to put in 100 milliliters into a person. And your instrument, your pump is set up at a rate of milliliters per hour. Sorry, I got that reversed. What is your rate you're going to put that in? Okay. All right, so we'll come back to that. Next one, how many moles is 30.4 liters of O2 gas at STP? All right. So again, we're at STP, we can use that ratio of 22.4 liters per mole. In this case, in this scenario, we're going to leave it with liters in the denominator because we want the liters to cancel out, leaving us with units of 1.36 mole, which again makes sense. Think about this. Look at you're given 30 milliliters, 30.4 milliliters. You are at STP, so you know that 22.4 liters of that 30 is 1 mole. So your answer should be a little bit more than 1 mole, and sure enough, you get 1.36. All right, now here you're given what is the mass of 4.5 liters of chlorine gas at STP. We're gonna have to add probably an extra step, right? Because we want to know, first of all, if we start off with 4.5 liters of chlorine gas, we need to convert to moles. Okay, here it is that any calculation to get from point A to point B, in this case, we want to go from liters to grams, we have to go through moles. So the first conversion factor, since we're at STP, tells us how many moles of chlorine gas we have if we have a volume of 4.5 liters. Then the next one would tell us how many grams of material we have, in this case, chlorine. Okay, we need the molar mass of chlorine. You have to realize that chlorine is part of the diatomic elements. So it's a Cl2. So we're going to take the 35.45 multiplied by 2. And that gives us a molar mass of 70.9 grams per mole. Check our units, liters cancel, moles cancel, leaving us with grams. Okay, so if I'm at a STP temperature in 1 atmosphere, 0 in 1 atmosphere, and if I had 4.5 liters of chlorine gas, that chlorine gas would weigh 14.2 grams. Okay. All right. This flow chart puts it all together, and this is only one flow chart that we're going to be using here. This is the one that deals with STP, but there's another one we're going to get to, which really is the culmination of these calculations that we're eventually going to be doing. So up to this point, remember, let's kind of put this together a little bit. We dealt with the elements, right? And then from the elements, we made ions to make ionic compounds. We put them together to make compounds. We talk about these compounds reacting with each other. Okay, we had 6 different reactions to make new compounds. Okay, and so then we talked about balancing those chemical reactions, and we talked about that because of conservation of matter, but more importantly, those balancing reactions gave us these ratios that connected, or gave us the ratios between reactants and the ratio between reactants and products and so forth, because we're going to use those to do calculations. But before we can do anything, we need to learn how to get to this important concept of the mole, because in order to get from point A to point B, we need to go through moles. So notice here in the center is the moles, because that's the key to get from left to right, bottom to up, whatever, whichever direction you need to get to. And so if we start off with the molar mass, if we start off with grams, for example, of some species, we need the molar mass. Okay, molar mass is grams per mole. And from the molar mass, we can determine the number of moles of that material that we're given. Okay. From the moles, now, if it's a gas and if we were at STP, guess what? We can calculate the volume, but only at STP. Okay. Or from moles, we can actually determine how many atoms and calculate how many atoms or ions or molecules or whatever we're working with by using Avogadro's number, because Avogadro's number, again, is nothing more than a ratio, 6.02 times 10 to the 23rd. Now, I made these arrows one way, but guess what, guys? It's really a double arrow. We can go in both directions. We can start down here in volume and work our way over. We can go in this direction. Start in volume of a gas and figure out how many atoms of that gas. Or we can start in volume and go the other direction and figure out how many grams of that gas, or vice versa. Or go directly from grams all the way across to figure out how many atoms we have. You see? So this whole flow chart kind of puts it somewhat together right now. We're going to have another one in the other chapter that it incorporates a lot of other things when we incorporate the chemical reactions. Okay, but this is the beginning. And the key aspect of all these calculations is having to go through moles. And then moles connects us from point A to point B, because we can't go directly from grams to grams. Okay. Normally, we don't have enough information to do that. We can theoretically if we got enough information, but 9 times out of 10 we don't. We only have part of the information. All right. So that flow chart's very, very important. Kind of summarizes all these calculations. So we can do some more calculations. Okay. The question is asked, how many grams does 17.35 liters of neon gas mass at STP? And then there's 2 parts. And there's how many atoms does this correspond to? Okay. Well, let's analyze the question first. Okay, let's break it down. It says how many grams? So that's what we're looking for. How many grams? What are we given? We're given 17.35 liters of neon gas. And what else they tell us? We're at STP. Well, given that we're in STP, I can quickly write, I can probably use this ratio, 22.4 liters per mole. Okay, let me change my color. It's kind of hard to see. Okay, so we need grams. We're given 17.35 liters, and we're at STP, so we can use this relationship. And what ultimately are we looking for? We're looking for grams. All right, so let's write down what we're given. Good way to start. 17.35 liters of neon gas. All right. We need to ultimately get to grams of neon gas. Oh, what does that tell me? Well, I'm going to need the atomic weight of neon gas, which top of my head, I don't know. I got to look that up. It's 20.18 grams per mole. So I think I got all the information I need. Got the atomic weight of neon gas. I got that I'm at STP. I start with liters. So, remember, I need to get to moles before I can get to anywhere. So I'm going, one way to look at it is I write down liters and I want to get to grams. Okay. Well, I can't do that without going through moles. I got to get moles first to get me from liters to grams here. And so I know that I'm at STP, so I can use this relationship for 1 mole. At STP, 22.4 liters, there's 1 mole is equal to 22.4 liters. So keeping track of my units, I'm canceling my units, I'm ended up with moles. Is it where I need to be? No, I need to get to grams. So obviously I got 1 more conversion factor where I got grams in the numerator and moles in the denominator. Okay, so that has to be our atomic weight. 1 mole, moles cancel. Unit wise, I'm left with grams, which is what I'm looking for. So I set that up properly. Now it's a matter of plug it into your calculator. Okay. So those are my factors, and I end up with 15.6 grams of neon. So 17.35 liters of neon gas at STP would weigh 15.6 grams. Okay. Now you could be asked the opposite question. You could be saying, you know, if I have 15.6 grams of neon, well, what is this volume at the STP? Well, we will go the opposite direction. Okay. Then finally, the next one says, well, how many atoms is this? All right. So we write down what we're given, 17.35. We need that factor, 22.4 liters, to get us into moles. And then instead of the atomic mass here, we need Avogadro's number, because that tells us how many atoms per mole that we have. So check my units, you know, all along. If you set this up properly, follow your units and make sure things cancel out. All right. And they do. Liters cancel, moles cancel. You got grams is what you're looking for. Atoms is what you're looking for the second part. Okay. Very similar, analogous to the conversion factors we did back with going from metric to English. Okay. You had conversion factors. You have conversion factors here. Keep track of your units. Use the dimensional analysis when you're setting them up properly in this manner. Try not to use the ratio system. Okay, the ratio system can mess you up a little bit if you don't follow through. If you get thrown for a loop in the first ratio, your whole answer's up in the left field there someplace. All right. All right, so now those are some examples. Now, with respect to density, we did talk about density, but now we can calculate the density to refresh your memory. Density was the ratio, another ratio, okay, of mass over volume, okay? Now, that is equal to also at STP again, we can determine the density of gases at STP by simply knowing the molar mass of that gas, and we know the molar volume because the molar volume at STP is 22.4 liters per mole. And so we know that the density of, let's say, ammonia would be 17.04 grams per mole, because the molar mass of the gas is 17. We got 3 hydrogens, 1 nitrogen, that tallies up to 17.04 grams. Okay. And then 22.4 liters per mole. Now you might think, well, wait a minute, how does that work? Well, look at the units. Oh, look at the units there, for example. We have units of grams per mole divided by liters per mole. Okay, so we're taking a fraction and dividing by a fraction. What do? When we divide by a fraction? We invert the fraction and multiply it. And so that is equal to grams per mole, invert the denominator. Okay, and so we end up with moles per liter. The moles cancel out, leaving me units of grams per mole. Okay. And so the density of ammonia gas at STP is simply 0.761 grams per liter, which is the ratio for density. Okay. In this case, we're using, normally the density we talked about before, it was grams per milliliter. But here, when we're dealing with gases at STP, it's grams per liter. You can convert that to milliliters. You still wouldn't be incorrect. Normally, we just keep it at liters when we're dealing with density of gases at STP. All right. So that density is pretty self-explanatory. We needed to calculate the, we talked about calculating the molar mass of a molecule, of a compound, right? We added up all the atoms and its contribution from each atom, how many, what's the atomic weight from each atom, et cetera, et cetera. Well, one additional bit of information that we can do is from the molar mass, we can calculate the percent composition, okay? And is basically, let's take water, for example. We know the formula of water is H2O, 2 hydrogens, okay? And which contributes 2.02 grams per both hydrogens, and then the oxygen contributes 16. So the molar mass total of water is 18.02 grams. Okay, just like the molar mass of any compound we need to make. Now, to determine the percent composition, we simply take the contribution of each particular atom and divide it by the total molar mass times 100. Okay. And for water, it turns out that there are 2 hydrogens and it contributes 11.2% hydrogen through the whole molecule of H2O. And the oxygen contributes 88.79% oxygen in the molecule of hydrogen. These numbers are true regardless of where you obtain water. If water has the formula of H2O, which to our knowledge, it does all over the world, even out in space, okay, you can analyze it, and if the analysis comes up to 11%, 11.2% hydrogen and 88.79% oxygen, unequivocally say, I got water in my hands. And we use this quite a bit in chemistry, especially in organic chemistry, when they're synthesizing, making new compounds. We know what we think based on other tests. We send a sample out, tell them to do a percent composition of carbon, hydrogen, sulfur, whatever you want, oxygen. And then when it comes back, you can back calculate to actually calculate the formula and verify that, yes, in fact, you made a particular compound by their percent composition. Then coupled with the other data, you nailed it. That's the structure, that's the compound. The percent composition all should add up to, roughly 100%. It's going to be a little bit off sometimes, 99.99, depends on your calculator, but it should all add up to 100%. If it doesn't, then check your numbers. Something didn't go correct. All right. So with that, let's do an example. You can take the percent, any compound that we throw at you and figure out its percent composition. All right, let's take this one, TNT, trinitrotoluene. Anybody know what that is? Heard of it? Good old-fashioned dynamite. All right, let me ask you a $6 million question. Does anybody by chance know who's responsible for TNT? Who made it? Okay, I'll give you a hint. Annually, there's a prize that goes out around the world for science, peace. Google says Joseph Wilbrand. I don't know, Skyler, but I think you might check that. He may have been part of it, but Nobel's the one noted, and it's possible. Who knows? But as far as I know, Nobel's the person responsible for TNT. In fact, TNT, once he brought it out, he made quite a bit of money, created a foundation, and created the Nobel Prize for medicine, chemistry, physics, peace, and so on and so forth. So anyway, trinitrotoluene, very difficult compound to make, obviously, because it's quite sensitive and quite challenging. Anyway, there's a general formula. It's got 7 carbons, 8 hydrogens, 3 nitrogens, and a total of 6 oxygens. Okay, so with that information, we can come up with the molar mass, and do use the Chem 130 periodic table for the atomic weights. Otherwise, your numbers would be a little bit different if not. Okay, so we got 7 carbons at 12.01 each. That's 84.07. 5 hydrogens at 1.01 each. 3 nitrogens at 14.01. 6 oxygens at 16. So that's 96.00 grams per mole. So the total molar mass is 227.15 grams per mole. Okay. So how many molecules of TNT would I have if I weigh out 227.15 grams of TNT? I have to weigh it out pretty carefully. How many molecules of TNT would I have if I weigh out 227.15 grams? 1 mole, which is correct, but how many molecules would that be? 6.02 times 10 to the 23rd. That is correct. A lot of molecules. No different than if I were to weigh out 2.02 grams of hydrogen. I would have 6.02 times 10 to the 23rd molecules of hydrogen. Okay. All right, so now we go in there and we determine the percent carbon, take the total amount of carbon divided by the molar mass. That gives us 37.01%. Hydrogen is 22.2%. Nitrogen is 18.5%. And then finally, oxygen at 42.26%. And that's what we normally would do if we were to make a compound as organic chemists and synthesize, send them out. And then we take this percentage and actually work it backwards to figure out the general formula. See, we're in the right direction. There's a lot of compounds that I sent out for analysis that did not come back as expected. So we have to go back to the drawing board and figure out what did we make. So anyway, try these at home, see how it works for you. How many liters would 3.425 grams of carbon dioxide gas occupy at STP? So you can see you got grams of carbon dioxide, you need to get 2 moles, okay? You got 2 factors you can use there. Second question, how many molecules are there in 3.425 molecules of carbon dioxide? You should end up with 4.68 times 10 to the 22nd molecules. And then finally, how many grams would be 3.0 times 10 to the 15 molecules of carbon dioxide mass? All right, it's a lot of molecules, but your final weight should be at 2.2 times 10 to the -7 grams. Very small weight. Okay. All right. Guess what, folks? You knocked out 2 chapters. All right. So the takeaway from this is this flow chart right here. Okay. And being able to calculate the molar mass, knowing Avogadro's number, which has units of units per mole, 6.02 times 10 to the 23rd. And knowing that at STP, that any gas occupies a volume of 22.4 liters. Okay. Oh, wait. Anyway, and so forth. So this flow chart will actually give you a good picture overall of this particular chapter. And then some more examples that we did using that flow chart. Density as far as gases at 0 degrees. Okay. It's just simply ratio of molar mass over molar volume. We know at STP molar volume is 22.4 liters. And then percent composition is we got to get the molar mass, calculate the molar mass of any molecule, that compound that we need, and then simply take the individual atoms in that compound, divide the total molar mass of the individual atoms by the total molar mass times 100, and that will give the percent composition. Okay. All right, and we did this example. You know, think about it this way. Sometimes this could be challenging, but let's figure out you're fully dressed, all right, and you got a total X amount of weight, and then just say 200 pounds, all right. So, yeah, when you're fully dressed, you can calculate the total weight of the weight your shoes bring in, right? Because you got your total weight. Your shoes maybe weigh 5 pounds, so 5 divided by 200 times 100. That would give you the percent composition of your shoes. You can do the same for every article of clothes that you're wearing to give you the percent composition of each one. This is no different. That's what you're doing. It's how many each atom brings in an X amount of weight through the whole molecule, and you're calculating the percentage that individual atom brings to, or atoms bring to the total weight of the compound. Okay, and it should add up to 100%. Okay, if it doesn't, and it will be 99.9-ish. That's okay. But if it adds up to like 80, then obviously you did something wrong with your math. Go back and check your math. All right, so try those at home. Other than that, congratulations. We got chapters 13, 4 more chapters, and they're relatively short too. All right. Any questions?